Welcome to our video tutorials for our PC tool openSYDE. In this video, we would like to introduce the topic COMM datapools. Based on the template application of the controller ESX4CSGW and by code generation with openSYDE, we would like to process CAN messages in an application programmed with the C development environment of logi.CAD. If you are not yet familiar with the basics of openSYDE and code generation, we recommend the videos First Steps with openSYDE and First Steps to C Code Generation with openSYDE from this series. For mobile machines, we need a system consisting of a controller, sensors and actuators, and communication systems for exchanging data between the components. The application on the controller plays a central role in this. STW supplies templates for such applications for every controller, suitable for every programming language, which contain the minimum code required to start the controller in a controlled manner and to enable data communication at various interfaces. Based on this so-called template application, the user can start to develop his own applications. Building on the template application, STW's PC tool openSYDE supports application development through code generation, i.e., based on device and configuration information about the system. This is conveniently compiled in the openSYDE project via the user interface. Code snippets can be generated and then used during application programming. An important part of this generated code is the data pools. There are different types for diagnostics, non-volatile memory, or hardware configuration. And there is one data pool type ready for simplified handling of CAN messages, the COMM data pool. For message transmission, there is the openSYDE communication stack. Through the communication stack, the content of received messages is stored in the data pool and extracted from it for the composition of messages to be sent. The communication stack is part of the software package provided in the target support package of the controllers from STW. Software deployment packages and the target support packages they contain are available for any programming language such as C or IEC 61131. In this video, we use the C perspective of the development environment logi.CAD provided by STW. Prerequisite for the generation of code suitable for the programming language by openSYDE is a corresponding code generator. By default, the generator for C code is delivered together with openSYDE. The CAN messages are assigned to a CAN bus. The meaning of the individual bits of a signal of a message and the properties of the message itself are managed in the openSYDE project. You can define the messages manually or import them if a definition file, for example of type EDS, is delivered with the device. In this video, we show how to transfer the CAN messages for temperature and status information of a temperature sensor into the variables of an application for the ESX4CSGW controller, and how we can display the values of these variables in a dashboard in openSYDE. Our experimental setup for this consists of the ESX4CSGW controller and a temperature sensor. For power supply, the devices are properly connected with the power supply unit. The sensor transmits its data to the controller via a CAN bus, which we provide with terminating resistors at both ends of the bus. The communication of openSYDE with the controller is done via the Ethernet. To be able to observe the data transmitted between the controller and the sensor on the CAN bus directly with the openSYDE CAN monitor at the end of the video, we connect the PC additionally to this CAN bus via a PCAN USB interface. In preparation for this video, we have downloaded the development environment logi.CAD version 3.13 and the TSP for the programming language C of the ESX4CSGW from the cloud on this PC and installed it in the default directories under CSTW. In the TSP, we can also find the user manual. The procedure shown in this video is also described there under the openSYDE server use cases. The preparation of the whole programming project starts with the creation of an openSYDE project. We map the presented scenario here. We walk quickly through the steps of creating the project. This is presented in more detail in the video First Steps with openSYDE. So we create a new project and add the components of our experimental setup, a controller ESX4CSGW from STW, and the temperature sensor T01 also from STW, and a CAN bus which we give a meaningful name. Controller and sensor are connected to the CAN bus. Finally, an Ethernet bus for later connection to the controller via the ETH2 interface. We also give this bus a meaningful name. We leave all values like node IDs and CAN speed at the default values because they also fit to the hardware used in this video. Therefore, the controller has the node ID 0 and the sensor the node ID 1. The IP addresses for the Ethernet interfaces are in principle freely selectable. However, we will match them to the values we will use in this demonstration. We will not use the Ethernet interface ETH1 in this project, therefore we deactivate it here in the openSYDE project. We save the project, and because of the logi.CAD IDE, we make sure that neither path name nor project name contains spaces or special characters. We wanted to use the Ethernet interface for access to the system by openSYDE. We changed to System Commissioning and therefore connect the PC in the standard prepared view with the Ethernet bus instead of the CAN bus. To test the experimental setup and to transfer the configuration defined so far in the openSYDE project to the hardware, we run the device configuration. We scan the network. The controller is found and we assign it to the topology node. We start the configuration. This was executed successfully, as we can see from the report. So the communication between openSYDE and the system works as desired via Ethernet, and the parameters have been set. The programming of our own application should always be based on the template application. For this we need the TSP of the ESX4CSGW for the programming language C, which is already installed on this PC, as already shown. In the TSPs there are the so-called openSYDE TSPs. We now import these into our openSYDE project for the controller and take a closer look at what is provided to us in detail with it. For the 3 cores of the ESX4CSGW, 1 data block each was imported. To keep the application as clear as possible for this video tutorial, we will only allow the communication of the controller with the sensor on the application core. Let's take a closer look at the details of the data block for the application core. It is a programmable project. The programming support is provided by the C code generator that is already supplied with openSYDE, as we can see from the path. Also, we can see the path to the programming project for the IDE, path and name of the resulting hex file, as well as a link to call the logi.CAD IDE in English with the C perspective. Since STW regularly provides new versions of the IDE, the path name for the call can be different and must be adjusted as here in the openSYDE project. Let's see what happened on the computer's hard drive because of this import process. Below the openSYDE project there is now a directory ESX4CSGW. It contains the complete logi.CAD project based on the template application for C, a subdirectory for the non-programmable boot core, as well as 2 directories for the programmable application and safety cores. For the application core we find in the result directory the hex file for the controller, and in the SRC directory the main C program. We now want to take a closer look at the project for the application core using the logi.CAD development environment. We start the ID from openSYDE. We open the project created by the openSYDE TSP import with the template application. logi.CAD should always use projects with unique names, so we assign a new project name in the context of this video tutorial and then run the clean function to eliminate problems caused by the renaming. So the starting point of the project is the program main.c. It starts with includes from the BIOS, followed by variable definitions until the main routine begins. This contains the initialization of the communication interfaces. The openSYDE server is then started, which enables us, among other things, to conveniently flash and use the data pools in connection with the dashboards in openSYDE. Finally, at the end there is a routine to constantly change the colors of the user LED. In this video, a logi.CAD shortcut with the keyboard is often used to open declarations. Here you can see in the context menu that opening or jumping to a declaration can also be achieved with the F3 function key as an alternative to the menu selection with the mouse. When we use this shortcut, we show the F3 key icon. Let's take a quick look at the initializations. It starts with Ethernet initialization. After the initialization of the Ethernet switch, built into the ESX4CSGW and the IWIP library, the interface itself is initialized. We can see that the template application first reads the IP address and other parameters from the EEPROM and then uses these values to configure the interface. This means that the IP addresses that we previously set with openSYDE in the device configuration are reused here. After the Ethernet initialization, all CAN interfaces are initialized. Finally, the openSYDE server is initialized. This consists of the initialization of the data pools and the diagnostic protocol driver for all communication interfaces. This allows us to later display the data pool values in dashboards in openSYDE, for example. At the end of the main routine, the intercore communication required for the multi-core system of the ESX4CSGW is programmed. You can see that there are some effects on the application on the safety core, although we plan to implement our application on the application core only. However, the controller only works if the applications on both cores and the boot core are coordinated and later flashed together onto the controller. As already seen, this is followed by the routine for controlling the LED. We can see that the template application has not taken any further precautions for CAN communication apart from initializing the interfaces. We will therefore return to this point later and program the necessary routines. Now we first want to take care of the CAN messages that the temperature sensor transmits. We return to our openSYDE project. As a minimum, a documentation must be available for the temperature sensor, which enables us to describe the message manually. Conveniently, in our case, we have an EDS file available in which the CAN messages sent by the sensor are described. So we import this file to openSYDE, assign the messages to the sensor, and get the description of a message with two signals. The first signal with 4 bytes contains the temperature values in degrees Celsius in different number formats. We can adjust the name accordingly. The second signal is used to transmit the status of the sensor. It is encoded here, for example, whether the measurement was valid or whether the sensor is in positive or negative overload. We will also adapt this name. In our system, both nodes will be involved in the communication, so we also mark the controller as active protocol node. We can see from the documentation of the sensor that it sends the messages with the CAN ID 180 plus node ID. In our case, that will be 181 and is therefore already configured correctly. 5 bytes are transferred, so we set the data length code to 5. We had already assigned the sensor as the sender of the data when importing the EDS file. We mark the controller as the recipient of the messages. By default, a timeout is used to receive messages. In order not to have to take timing into account during the video, we deactivate this timeout. As a result of this process, so-called COMM data pools have now been created by openSYDE. For the sensor, this is just the CAN message according to the OSI Layer 2 protocol. Since no programming and protocol support is provided for the TO1 by openSYDE, there are no further functions here. Programming support is provided for the ESX4CSGW controller, and we also want to use it. Our simple example in this video is not programmed under safety conditions and is therefore limited to the application core. Therefore, we select this application as related data block. We can now use the generate files function to generate code for C programming. To do this, we should first save the changes we have made. In this generated code, all data pool elements, in this example the CAN messages, are created as variables. The name of the signals in the CAN message is used for the names of the variables. This code can be reused in the application. The variable is later filled with the contents of the CAN message during operation. openSYDE indicates that code is only generated that matches the active configuration. All previous generations are deleted and only the current files are created. We see that this has a direct effect in the project directory of the logi.CAD project. Before we can continue working with the code we just created, we must put the openSYDE communication stack into operation. This allows us to receive the CAN messages from the sensor and write the payload data to the data pool. This saves us from having to deal with each message individually with CAN functions of the BIOS. We can later use the data pool elements directly in operation, for example, react to certain values in the program flow or display them in a dashboard in openSYDE. STW provides the necessary programming as part of an example. We therefore simply copy the files ozapp.comc and ozapp.comh from the example in the TSP into our project. We'll look at the programming in these files in the development environment in a moment. To do this, we first update the project in the IDE. The example in the TSP is much more detailed than we need in this video. We therefore remove the unused program parts. The example in the TSP considers other protocols as well, but we can only use CAN Layer 2 and not the STW protocols ECES and ECOS. We include the required headers. Defines for RX filters follow. Here we only need filters for CAN Layer 2. We will not go into the macros used here in the context of this video. However, we must adjust the value of the filter for the CAN IDs used here, since our TO1 uses CAN ID 181, but in the example, it is only filtered from CAN ID 300. Then we initialize the communication stack with the function ozapp.com_init. For the sake of simplicity, we will not use any further data pools for the time being, and therefore delete the associated program lines of the example. This is followed by the initialization of the COMM engine. We'll take a quick look in the manual to see what's required. 3 parameters are expected: a constant generated by openSYDE, 2 structures for buffer and CAN application for intercore communication. These parameters are described with the support of macros, for which we will not go into detail here. The global variable previously generated by openSYDE in the generate file step can be found in the openSYDE generated area of the project. We limit ourselves again to the communication with the only defined CAN interface number 1 in our project and therefore delete the initialization of the COMM engine for CAN 2. Since we only work with the CAN Layer 2 protocol, we remove the program lines for the other protocols. Now the COMM engine can be started. The required parameter can already be found in the code generated by openSYDE. We still remove the start of the COMM engine for the second CAN interface. The OSI app COMM cycle function is used to handle the COMM stack. Since we only want to receive CAN messages in our video, we delete the program lines for sending messages. We have now arrived at receiving the messages. Reception on the first CAN interface is triggered. We delete the call for the second interface. This function breaks down the received message and saves the payload data in the COMM data pool, which has been automatically generated by openSYDE. We then check the status of the received message, i.e. the message that the TO1 sensor sends. In the TSP example, this is a different message, which is why an error message is displayed here. But openSYDE generated this variable. We look in the associated header file and find the name for the CAN message of the sensor. We now insert the name of our message instead of the name of the TSP example. We can now proceed with either error handling depending on the status of the message, or process the content of the message. First, we delete two program lines that we don't need because we don't use the data pool from the TSP example. Then we read the payload data from the COMM data pool into a variable, i.e. the temperature of the TO1. In the same way, we read the status of the TO1. Of course, we must declare the variables. We now set ourselves the additional task of providing the error-free received data of the CAN message in another data pool of the diag type. We only do this for demonstration purposes. In a real application development, we could continue to work directly with the data from the COMM data pool. So let's go back to openSYDE and set up such a data pool. We use a data pool of the diag type, which is suitable for monitoring such values and later displaying them in dashboards. We give a descriptive name and assign it to the application core. We also give the list of variables in this data pool a descriptive name. The names of the variables in these lists are also given descriptive names. A variable for the temperature, which we expect to range from 0 to 100 degrees. And a variable for the status of the sensor. We generate the code. Let's go back to our IDE and update the project. We recognize the C and H files for the new data pool. In the C file, we see, among other things, the list definition with our two variables for temperature and status in the code. To be able to use the new data pool, we include it in our program. Now we fill the diag data pool with our received data from the CAN message, i.e. the COMM data pool. Now let's delete the program parts of the example for the second CAN interface that we don't need for this video. Likewise, the reset handling for receiving messages, since we don't deal with the timing in the video. For our OSI app COMM, no errors are displayed anymore either. We must now ensure that this code of OSI app COMM is called cyclically. In the main routine, we see the start of the openSYDE task. This consists of several initialization steps, as in the example of the TSP of the ESX4CSGW. We place the call to our initialization after the initialization of the diagnostic protocol driver. After starting the openSYDE main task with the diagnostic protocol drivers on all channels, we can also start our communication stack. This now ensures that we cyclically update our data pools with the temperature and status values of our temperature sensor. Finally, we must include the OSI app COMM. We can now build the application in the development environment. First, we save the project. Since we have dependencies between the applications on all cores with multi-core controllers, such as ESX4CSGW, we build all applications. We switch to openSYDE and update the controller with the new hex files. To do this, we go into the update mode in System Commissioning. openSYDE uses the grey symbols to indicate that there are newer hex files than are currently on the controller. We start the update. The controller now has the new applications. The ESX4CSGW is reset using exit update mode, and the new application runs on the controller. We now want to visualize the transmitted values for temperature and status in a dashboard using the data pools. So we drag a widget for the temperature value onto the dashboard. Also a widget to show the status. Both widgets are not configured yet. By double-clicking on the widget, we are offered all data pools as possible data elements for the widget, and we select the appropriate element from the diag data pool for the temperature. As said before, we could also use the COMM data pool for the same result. We do the same for the status. We save the project and immediately go online with the dashboard. We see the temperature value and the status value of 0, from which we can read from the sensor manual that this status means that the measurement of this temperature is valid. We can also see that the measured value changes when the temperature changes. Since we look at the data pool values in the dashboard, we see the values that the application on the controller also works with. In addition, we can directly monitor the values that are transmitted on the CAN bus using the openSYDE CAN monitor. We load the openSYDE database of our project into the CAN monitor to display the plain text names. In comparison, we see that the transmitted values and the data pool values visualized in the dashboard are the same. We hope that we have brought you a little closer to the topic of code generation with openSYDE for CAN communication and using data pools. We summarize. We have described our system in openSYDE, including all CAN messages. We have defined COMM datapools and diag datapools. We have generated C code from it and used it for programming with the IDE logi.CAD. We wrote the payload data of the CAN messages into the datapools with the help of openSYDE specific functions and used them in our application. We built the application as a hex file and put it into operation on the controller. We were able to display the data pool elements in the dashboard in openSYDE and compare them with the data on the CAN bus. In the series of openSYDE videos, other videos appear on this channel that deal with the details of individual features. We wish you every success in using openSYDE.